Hello, everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to continue with the chapter P block elements, and we are going to continue with group 14 elements. And particularly, we will be discussing carbon, that is the first element of group 14 in detail, where we'll be discussing the anomalous behavior, that is abnormal behavior, that is shown by the first element of this group, that is carbon, and the various allotropes of carbon that exist in nature. Before we begin, a piece of information for you. You can use the coupon codes Mission J or Mission Need while you enroll at First Online University for Mission J or Need in order to avail good discounts. Let's now firstly begin with the anomalous behavior of carbon. Now, I've already told you what is anomalous behavior. It is the behavior that is shown, which is different from the behavior shown by the rest of the elements of that particular group. And usually the first element of a particular group is going to show an abnormal behavior or abnormal properties. That is why we call it as an anomalous behavior as compared to the rest of the elements of the same group. So when we talk about carbon, why does carbon have to show anomalous behavior? There are various reasons for that, and these reasons are very, very important. First and the most important reason is the absence of d orbitals. Now, whenever we talk about the presence or absence of d orbitals play a very important role in deciding as to what covalency a particular element can possess. I mean, how many um, uh, atoms can it bond to, then what are the various many properties are going to be decided by the presence or absence of d orbitals. And since carbon does not have d orbitals, that is why it shows anomalous behavior, because rest of the elements do have d orbitals. Then it has a very small atomic size of just 77 picometers. It is also very highly electronegative, and the electronegativity is 2.5. It has also very high ionization enthalpy, which is owing to the fact that it has a small size. The value of ionization enthalpy is 1086 kilojoules per mole. Next reason is the presence of only 2 electrons in the penultimate shell. I've already told you what is penultimate shell. The outermost shell is the valence shell, and the shell just before the outermost shell is the penultimate shell. And in the penultimate shell, there are 2 electrons that are present. Only 2 electrons. Okay, so these are the 5 reasons which are responsible for giving carbon an anomalous behavior. Now, what are the important trends that are observed? Firstly, because of the small size and also the lowest atomic volume of carbon, carbon becomes the hardest element in group 14. Okay. Next is that carbon has the following highest amount. So when we talk about group 14, what are all the properties that carbon has the highest? Okay. These are 5 properties: melting point, boiling. You have to learn this, okay? Melting point, boiling point, ionization enthalpy, highest catenation. Catenation is a tendency that is shown only by carbon, okay? So highest catenation of all the elements and highest electronegativity. So these are the 5 properties which we can say that carbon has the highest value as compared to all the other elements that are present in the same group. So we can look at the atomic radii. We see here that, so we have talked about melting point, boiling point, and the rest of ionization, enthalpy, catenation, and electronegativity. Apart from these 5 properties, or amongst these 5 properties, if we see the atomic radii, first of all, is the least for carbon, which is just 77 picometers, and it is intermediate for germanium, which is 122 picometers, and highest for lead, that is 146 picometers. And if we see down the group, there is an increase in atomic radii with no exceptions present. Because what do we know is, as we go down the group, new shells are going to be added, and therefore the atomic radii is going to increase. The next property that we are looking at is the electronegativity values. And if we see, for carbon, the electronegativity is highest, that is 2.5. As we are moving down, the electronegativity decreases, but it almost remains constant for silicon, germanium, and tin. And for lead, there is a marginal increase. We have already talked about electronegativity in detail. Next, we move on to the ionization energy values, and we see that carbon has got the maximum IE value, and then the IE value goes on decreasing as we go down the group. But there is an exception that is seen as we go from tin to lead. there is a marginal increase that we see in the IE value. So all these things we've already discussed in the previous lectures where we were talking about group 14 elements. The third is when we talk about the absence of d orbitals, it has no tendency to form complexes, and therefore the maximum covalency that it can have is just 4. The presence of d orbitals also is important in terms of allowing the element to expand its covalency to be able to have a covalency say equal to 6 or at least more than 4. But carbon has a maximum covalency of 4. If you look at the electronic configuration, it is 1s2, 2s2, 2p2. So there are no d orbitals present. The ground state would be 1s2, 2s2, 2p2, that is 2 electrons are present in one p orbital each. Now what happens is that one electron is going to make a jump from the 2s to the 2p orbital, that is in the excited state. ES means excited state, GS means ground state. We have seen that before, so I'm not like I'm like still repeating it. So then what do we see is that now here we have 1 electron in 2s and 3 electrons in 2p. So it gives sp3 configuration to carbon. So what do we see is that carbon forms p-pi multiple bonds with itself and others because there are 3 electrons present in the 3p orbitals. Therefore, there is a tendency of carbon to form 3 p-pi orbitals, 3 p-pi multiple bonds, either with itself, that is carbon-carbon triple bond, or with some other element it can do so. For example, if we have carbon double bond oxygen or carbon double bond sulfur, we also have carbon triple bond nitrogen. Other elements are not capable of forming p-pi bonds because their atomic orbitals are too large to diffuse. Because as we go down the group, the size of the p orbitals will also increase. 3p orbitals are going to be bigger in size than 2p orbitals. 4p are going to be further bigger in size as compared to 3p or as compared to 2p orbitals. So it is only possible with the 2p orbitals that we can have this p-pi multiple bonding. Then also carbon shows a very strong tendency of catenation by virtue of which it is capable of forming thousands of compounds. So if you can, if you look at organic chemistry does not exist without carbon. Carbon is capable of forming thousands of compounds because it has a catenation tendency. What is catenation tendency? It has a tendency to form long chain compounds. Okay, CC bonds can go on occurring and we can have so many compounds being formed, and these CC bonds are also very strong. So what is catenation? The property of self-linking of atoms of an element, that is carbon-carbon atoms, will go on self-linking with each other to form straight chain or branched chains or rings of different sizes by covalent bonds. That property is called catenation. You can have a look at these structures. We have already, in class 10th, in the chapter carbon and its compounds, we have discussed the property of catenation in detail there. Just the revision is what we are doing here. So it's like if you can have a look, the first structure is that of graphite. So we have different graphene. It's like one sheet of graphite is called graphene. So different graphene sheets are joined together through covalent bonds to form what we have as the structure of graphite. Then we can have a look at the structure of diamond, and a diamond ring is also shown so that whatever diamond is present is actually having this very closed pack structure. And then we have Buckminster fullerene, which is the C60 allotrope of carbon. See, these are basically these graphite, diamond, and Buckminster fullerene are allotropes of carbon, which we'll be taking up in this lecture itself, but at a later stage. Right now, we are discussing the anomalous behavior of carbon. Next important trend is so we have already discussed about it. Okay, catenation is something which we have discussed. Now, as we go down the group, the size increases and electronegativity decreases, because we know that down the group, electronegativity decreases, across the period, electronegativity increases. And therefore, as we are going down the group, since electronegativity is going to decrease, the tendency to show catenation will also decrease, because see, catenation tendency we have already seen that carbon has the maximum or the strongest tendency to show this property of catenation. Why is it that the other elements of the same group are showing less catenation tendency or no catenation tendency at all? Is because of the decrease in electronegativity. Now, when the electronegativity will decrease, it will have an effect on the bond strength. CC bond strength is very high, and therefore it can go on forming long chains, which can be straight or branched chains, or they can also form rings. But when the bonds are not going to be strong, this catenation tendency is going to be reduced. And this can be understood by the bond enthalpy values also. So if we look at the bond enthalpy values for carbon-carbon bond, it is 348 kilojoules per mole. For silicon-silicon, it reduces to 297. For germanium-germanium, it reduces to 260. For tin-tin, it reduces to 240. And for lead-lead, it is just 81 kilojoules per mole. Okay, so I've already told you the reason. Therefore, the order of catenation would be carbon, which is very, very greater than silicon, which is greater than germanium, which is approximately equal to tin, which is like very, very greater than lead. So lead does not show any catenation at all. The bond enthalpy is so less that it will not show any catenation at all. Okay. Now, based on this, let's have a look at few MCQs. Which element exhibits the highest catenation property? We have already discussed that it is carbon. So option D is the correct answer. Next question is, which of the following ion will not exist? SnF6 2 minus, germanium F6, silicon F6, or carbon F6. See, you do not have to go into details of learning or memorizing these, the existence of these compounds. All you need to know is that carbon, because of the absence of d orbitals, can show a maximum covalency of just 4. Therefore, CF6 2 minus cannot exist. So option D is the correct answer. Next, we move on to the allotropes of carbon. Now, in the allotropes of carbon, we have already discussed, we have not discussed, but we have at least seen the structures of graphite, diamond, and Buckminster fullerene. These are the three important allotropes of carbon which we have been studying till now and which we are going to take up in this particular lecture also. So, now, why is it that, first of all, why is it that only carbon is showing different allotropes and not the rest of the elements of the same group? This is because we have already seen that as we go down the group, electronegativity decreases, catenation tendency decreases. So it is only carbon which has the catenation tendency as well as the tendency to form p-pi multiple bonds, that it has the possibility of existing in various allotropic forms. Now, what are the allotropes of carbon? There are two things that we are going to talk about: crystalline allotropes and amorphous allotropes. In crystalline allotropes, we have diamond, graphite, and fullerene. And these are the pictures that you can see. And in the amorphous allotropes, we have charcoal, which is further subdivided into wood charcoal, which is in the picture, and animal charcoal. And we have lamp black. Okay, so all these pictures I have given along so that you have this picture in your mind while we are actually talking about all of these allotropes in detail one by one. So let's first start with the crystalline allotropes, that is diamond. Now, as you can see in the picture, diamond is something which is very lustrous, it is shiny, and it's, very attractive. But what is it that goes, the chemistry behind it? Okay, so that is what we are going to talk about. Diamond has got a crystalline lattice and therefore it's the crystalline allotrope of carbon, and it has a 3D network structure. If you look at this structure, these gray dots are basically representing the carbon atoms, and these red bonds are the covalent bonds that exist between these carbon atoms. And this is how the structure of diamond looks like. Okay, so carbon-carbon bond length in diamond is 154 picometers, which is an important data to remember. And so this bond length is 154 picometers. The next thing that we need to know here is that each carbon atom, and here the carbon atom is sp3 hybridized. Each carbon atom is linked to 4 other carbon atoms. So you choose any one carbon atom. Suppose we choose this carbon atom. So it is linked to 1, 2, 3, and 4 other carbon atoms in a tetrahedral shape or fashion by covalent bonds, and the covalent bonds have a length of 154 picometers. So we have a tetrahedral geometry, sp3 hybridization, tetrahedral geometry, 154 picometers. These are the important, and each carbon atom is linked to 4 other carbon atoms. These are the important details that we have discussed till now. Now, since all the four valence electrons of carbon are involved in bonding, so there are no free electrons present, and therefore, because of the absence of free electrons, it is a bad conductor of electricity, because it is due to the movement of electrons or ions that electricity can be conducted. Since there are no ions present and since there are no free electrons here, so it's a bad conductor of electricity. The electronic configuration of carbon is 1s2, 2s2, 2p2, and in the excited state, one of the electron goes to the 2p orbital, one of the empty 2p orbital, and the hybridization that we have is sp3. The diamond is the hardest substance that is known on Earth. Okay, remember, this is an important factual information. Now, what are the uses of diamond? Precious stone used in jewelry and ornaments. That is the most common use that we know. Then it is also used as an abrasive for sharpening hard tools. It is also used in the manufacture of tungsten filaments for electric bulbs, used for making dyes and for rock drilling. Now, for diamond, we also need to know the fact that it is covalent and yet it has a high melting point. Why? This is because diamond has a 3D network which has very strong CC bonds, and these CC bonds are very difficult to break and a very high temperature is actually required for this purpose. Therefore, it has a high melting point. Based on this, let's quickly have a look at few MCQs. Carbon exhibits many allotropic forms because catenation property, yes. P pi P pi bond formation, yes. So both A and B, option C is the correct answer. Next question is carbon in diamond exhibits what hybridization? We have discussed in detail. It exhibits sp3 hybridization. Option C is the correct answer. Next question is why is diamond very hard substance? Because it has covalent nature, because it has ionic nature, it's a giant molecule, crystalline lattice and 3D network. Yes, that's the correct answer, option D. Next we move on to the next crystalline allotrope of carbon, that is graphite. Now when we talk about graphite, graphite is basically having layers, and this time these layers are not joined together by covalent bonds but by van der Waals forces of attraction. If you carefully see, you can have a look at these various black layers, and these are going to be joined together by simple van der Waals forces of attraction. Okay, a clearer picture is shown here. So when you do not have proper solid lines representing the bonds, but you have dotted lines, that clearly tells you that these solid lines are covalent bonds and these dotted lines are basically the van der Waals forces of attraction. These black dots are carbon atoms and these blue lines are weak van der Waals forces of attraction which are holding the layers together. These are graphite layers, okay? Layer lattice structure of graphite is what is shown here. The distance between any two layers is 340 picometers or 3.4 angstrom, okay? This red double arrowed line is what is telling us this fact. Each layer is composed of planar hexagonal rings of carbon atoms. So if you can see, there are 6 carbon atoms in one ring. So that's going to be like hexagonal rings. And since they're all in one plane, these are called as hexagonal rings, planar hexagonal rings of carbon atom. And there are many such layers, such planar rings, which are forming layers to form the structure of graphite. Okay. Now, carbon-carbon bond length within the layer, if you can see the black solid lines, they are actually representing the carbon-carbon bond, which is having a length of 141.5 picometers or 1.415 picometers. Okay, this blue line is actually representing that distance. So, in graphite, each carbon atom is sp2 hybridized. Remember, in diamond, each carbon atom is sp hybridized because it has a tetrahedral structure. But in graphite, since each carbon atom is having a planar structure, so it's going to be having a bond angle of 120 degrees and therefore sp2 hybridized carbon atoms. So 1s2, 2s2, 2p6 is the 1s2, 2s2, 2p2 is the electronic configuration in the ground state, and in the excited state it becomes sp2 hybridized. So what happens is it is just 1s and 2p orbitals that are getting utilized in bond formation. So in graphite, the fourth electron is responsible for forming a pi bond. Okay, so if there was this question in your mind that where does this fourth electron actually go, it goes into forming a pi bond. So the electrons are delocalized over the whole sheet and these are mobile electrons, and since these electrons are capable of moving, therefore graphite is a good conductor of electricity. So that's the difference between diamond and graphite. So when we talk about the uses of graphite now, it is a soft and slippery substance, so it can be used as a dry lubricant instead of oil, as you can see in the picture. Then it can conduct electricity, and therefore it is used to prepare electrodes. We have graphite rod that is used as an electrode. Then when mixed with wax or clay, it is used to make cores of lead pencils. That's the most common use of it that we know. Then it is also used in the manufacture of dry cells and batteries, as you can see in the picture. Now let's do a few MCQs based on this. Hybridization and structure of carbon and graphite. Hybridization we know is just sp2, and it has a layered lattice structure. So option B is the correct answer. Next question is, lead pencils contain what? Lead, carbon, graphite and clay, or carbon diamond? It is graphite and clay. So option C is the correct answer. Next question is, graphite is a good conductor of electricity because of the presence of crystalline structure, sp2 hybridized carbon, free electrons or free atoms. See, remember, even if you do not know the reason, or you do not remember graphite for any damn reason, you should know that it is always because of the presence of free ions or free electrons that electricity can be conducted, and therefore here option C is going to be the correct answer. Next question is the carbon-carbon bond length and distance between adjacent layers in graphite. So I told you all these facts are very, very important. So carbon-carbon bond length, we know it was 1.415 angstrom, and the adjacent layers were having a distance of 3.35 angstrom. So option C is the correct answer. The way I remembered this information, you can easily remember it. Next, we move on to the next crystalline allotrope of carbon, that is fullerenes. Now, if we look at fullerenes, the structure of fullerene was actually given by these two scientists, that is Malley and Cort. Okay. So the family of spherical carbons, it's like a cage. Okay. It's like a football structure that you have. It's a cage. So spherical carbon cage molecules are known as fullerenes. Okay. The structure is compared to a football. Now, how are fullerenes prepared? When graphite, okay, the layered structure is going to be heated in an electric arc with an inert atmosphere, that is, we do not have oxygen present, we either have helium or neon present. Then a soothing material is going to be formed by the condensation of the vaporized CN molecules. CN means there are so many, okay, molecules. It's like a polymer of it that exists, and these are known as fullerenes. So this is the entire setup that we have for the preparation of fullerenes. There's a quartz pot, and we keep graphite in that, and we have a furnace to heat it, and the atmosphere is that of helium or neon. Now the major quantity is that of C. Now here Cn is basically C16. Major quantity is C60. Traces of C70 or traces of fullerenes consisting of even number of carbon atoms up to 350, like C540, are also seen, being formed, but majority we have C60. Now note that superconductivity is a phenomena of exactly zero electrical resistance. So when we say a substance is a conductor, that means it is conducting heat or it is conducting electricity, but there is some sort of a resistance still being present there. But when we talk about superconductivity or superconductors, it means there is zero resistance present, and exactly zero electrical resistance and expulsion of magnetic fields occurring in certain materials when they are cooled down below a characteristic critical temperature. See, I'm not going to go into details of superconductivity that you will be studying in physics. What is superconductivity? What is critical temperature? Just understand that there is one particular temperature below which, if we cool the substance, it is going to exhibit superconductivity. Now, fullerenes being covalent are readily soluble in organic solvents. Clear? Next is fullerenes react with group 1 metals forming K3C60 solids, which behave as superconductors below 18 Kelvin. So you can see such a low temperature. 18 Kelvin is such a low temperature, and fullerenes are capable of existing as acting as superconductors below this temperature. Now, C60 molecule has a shape like a soccer ball, and therefore they are called Buckminster fullerene or buckyballs. Okay, because they are similar to soccer balls. It consists of 6 membered rings. The number of 6 membered rings are 20 and the number of 5 membered rings are 12. Remember, this is very, very important. And the CC bond length is approximately 143 picometers and the C double bond C bond length is approximately 138 picometers. Now, again, note that the 6 membered rings, which are 20 in number, are so 6 membered ring is fused with 6 or 5 membered ring, but a 5 membered ring can only be fused with a 5 membered ring. Now, carbon atoms undergo sp2 hybridization, and each carbon atom will have 3 sigma bonds with other carbon atoms, and the remaining electrons are responsible for the aromatic character. There are 60 vertices present, and each one is occupied by one carbon atom. Note that graphite is thermodynamically most stable allotrope of carbon, and therefore delta HF, that is heat of formation value of graphite, is taken as 0. And for diamond and fullerenes, it is 1.9 and 38.13 kilojoules per mole respectively. This is also an important data. Let's have a look at few MCQs quickly. The formula of first well-known buckyball is C40, C50, C60 or C70. So it is C60. Next question is structure of fullerene, cricket ball, volleyball, tennis ball or soccer football. Option D is the correct answer. How many number of 6-membered and 5-membered rings are present in C60 respectively? So 20 and 12. We have studied that. Option A is the correct answer. Next question is the carbon in diamond graphite fullerenes undergo dash hybridization. So we know in diamond it is sp3 hybridized, in graphite it is sp2 hybridized, and in fullerenes it is sp2 hybridized. So option A is the correct answer. This was very, very important. So it is only the crystalline allotropes of carbon that are important from the examination point of view, but I've already told you at least the names of the amorphous allotropes, so that is something that you can easily just remember the names, okay? Nothing else is important from examination point of view. So this lecture contains a lot of important information. Every statement, every sentence that I have spoken, I have made you people understand is important from examination point of view, because everything that we have studied has come in the form of questions. Okay, I've included all the important concepts in this particular lecture. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app through Google Play Store or App Store for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.